Uh, Good morning, ladies and gentlemen. Thank you very much for your time and interest in being in this session with me. The session I'm going to present in the next 15 minutes or so our work with my colleagues, Dr. Marcos Santos and Mr. Igor Pinheiro. The presentation is titled Analysis of the Gaussian AHP Method in the Light of the Pareto Front Obtained Through the Multi-Attribute Tradespace Exploration Method. It's a case study, okay? I don't know how many of you have had access to our full paper, which was made available at the website of the web conference. Anyway, I will do a briefly explanation of our objective in this work. Our objective was to verify the relation of the ranking produced by the Gaussian AHP method with the Pareto front produced by the MADE method for the same attributes and for the same design alternatives, and to discuss an improvement proposition for the Gaussian AHP method, which, by the way, was a method proposed in the same conference last year by a group of researchers, Brazilian researchers, in a seminal paper published here in the AHP conference in 2021. But the original case study that we were going to discuss today was proposed by Professor Adam Ross in 2014 at the MIT Systems Engineering Research Initiative. And the objective of the work of the case study was to analyze many design alternatives for a new space tug. A space tug is a type of equipment, a space equipment, used for modifying parameters of another space equipment, like satellite, for example. And if you want to increase or decrease the orbit of a satellite, one of the methods that you can use is space tug. So the case study used the MADE method, multi-attribute Tradespace exploration, which was proposed by Professor Adam Ross and Professor Nathan Diller while they were working at NASA, based on the multi-attribute utility theory developed by Ralph Kinney and Howard Rafa in 1976. Well, it's not the objective of this presentation to discuss in detail the MADE method, but rather to discuss the a new proposition for the Gaussian AHP. Anyway, I have to describe a little bit of the MADE method. It's based on a concept called multiple attribute utility, which is it's a form of you consolidating many utility functions in just one utility function. It's very useful when you have when you want to generate, for example, a bidimensional Pareto front rather than using a multi-dimensional Pareto front. So using the multiple attribute utility, you can do that with easy. It's a summation of n1 from 1 to n, where uppercase n the number of attributes of the multiplication of the single attribute utility of each attribute by the weight of each attribute. And you do that for each one of the design alternatives. And you have a collection of m, uppercase m, design alternatives. And then you obtain the multiple attribute utility. And solve is the single attribute utility calculated for attribute n of the design alternative m. And weight is the weight of each one of the attributes. So in the original case study, the group of Professor Adam Ross selected 3 design alternatives. Actually, they had the opportunity to use many, not design variables, but attributes, performance attributes. They had the opportunity to select many performance attributes, but they at the end selected only 3 performance attributes. I'm not going into details of the method used for selecting the attributes. It's not important for the result of our work. I have only to describe, to call the attention for. Looked at the assigned weights for each attribute. Weights were obtained by a committee of subject matter experts, and each attribute have some points of interest, some levels of interest. I have to say that these attributes do not have to be linear, but they have to be monotonically increasing or decreasing, right? And for each one of the levels of interest, there's one single attribute utility value. For example, for the level of interest 0, we have the single attribute interest 0. And for the level 12, we have the single attribute utility 1. And to intermediate levels, we can do piecewise interpolation. And so on and so forth for the other attributes, delta V, capability, and response time. Note that for the response time attributes, we have a monotonically decreasing attribute. So the level 0 corresponds to the single attribute utility 1, and the level 1 corresponds to the single attribute utility 0. They could have considered many cost attributes, but they only considered just one cost attribute, which was the total cost of the project in millions of US dollars. And these are important. These are the design variables they considered. They used a technique called DVM, design value matrix, to select the variables, the design variables which had the most impact into the performance attributes and cost attributes. And those variables were payload, propulsion type, and fuel level. As you can see here, they also attribute some levels for each one of the design variables. And the reason is they want to perform a full factorial of each one of these levels to generate many design alternatives. So if you have 4 levels for the payload variable and 4 levels to the propulsion type level, variable, and 6 levels for the fuel level variable, at the end, when we do a full factorial combination, you have 96 design alternatives. And the objective is to position these design alternatives into a bidimensional graph to analyze the location of each design alternative in relation to a Pareto front. They also used some auxiliary variables. I'm not going to description of, it's not for interest of this presentation, and some constants and some formulae. Our group used these formulae and auxiliary variables and variables to generate an application for generating the full factorial of the all design variables, and to generate the AHP, the Gaussian AHP method ranking, okay, and to compare the two results. And so this is the result of the mate method. We have in the horizontal axis the normalized total cost, and in the vertical axis we have the multiple attribute utility. And here each dot represents a design alternative. We have here 96 design alternatives, which are the resulting of the full factorial of those design variables that you saw in the previous slide. And you can see here a Pareto curve, Pareto front in red, and you can see that some points of the design alternatives coincides with the Pareto front. Those points are the most optimized points, and you should rationally, for example, to choose this point harder than this point, because if you choose this point here, you are going to choose a point with a higher cost for the same level of multiple attribute utility. So the points in the red cube are the more rational points you have to consider in your design analysis. So let's briefly remember the Gaussian AHP method. As I said before, it was a method proposed last year in this event, in this conference. And the Gaussian AHP method, it produces a ranking that's the inner product of each point, in this case, each attribute of each design alternative, and the transposed normalized standard deviation vector of each attribute. And the result is sorted in decrescent order. This is a method that you can use when you don't want to perform pairwise comparisons. You can use this technique to so many variables you want, so many attributes you want. Okay, it's not the objective to enter in details about the Gaussian AHP method, but you can refer to the paper from the Santos and Elia, which is referenced in our full paper, which is available in the web conference. So after we generated the 96 design of alternatives with the mate method, we were now performing the study of those alternatives in the light of the AHP method. Okay, from the 96 design alternatives that were generated by the mate method, constituted of two attributes from monotonically conflicting utility functions, which were total cost and multiple attribute utility, and having 11 points in the Pareto front. If you can count here, we have 1, 2, and 3, 4, 5, 6, 7, 8, 9, 10, 11 points in the Pareto front. And those design alternatives and attributes are then submitted to the Gaussian AHP method. And interestingly enough, 7 points within the range, the first to the 12th of the Gaussian AHP ranking, coincided with the Pareto front. As you can see here in the next slide, we have in this graph 10 points of the Gaussian AHP ranking coinciding with the Pareto front. In the other hand, the original Gaussian AHP ranking, only 7 points coincided with the Pareto front. We also are proposing a modification to the original Gaussian AHP method. And the modification we are proposing is we are, rather than using the inner product for producing the ranking, we are proposing to use the bivariate Gaussian probability mass function of each point sorted in crescent order. Since the points in the extremities of the feasible region have lower probability mass function values than points near the center of the feasible region, they will appear first in the ranking. So if you look at this picture, the points in the extremities of the feasible region, which are these points and these points here, have lower probability mass function values than the points in the near the center of the feasible region. So it's more probable that points with lower values of probability mass functions will coincide with the Pareto front. It was the case in this specific case study. Okay, it's not guaranteed that will happen in all situations. That's what we are saying here. For this case study, the first 12 points of the ranking produced by modified Gaussian AHP method are closer to the Pareto front than using the original Gaussian AHP method. As I said, when you used the original Gaussian AHP method, only 7 points coincided with the Pareto front. When we used the modified proposition, 10 points of the ranking generated by the modified Gaussian AHP method coincided with the Pareto front. We have to do this disclaimer, as in the original Gaussian AHP method, it's not guaranteed that the first points in the ranking will coincide with the Pareto front. For example, if you take another very popular method like the electric 2, it's guaranteed that the first points of the ranking generated by electric method will coincide with the Pareto front. Okay, so that's all, folks. Thank you very much for your time and interest, and Now, if you have any question, I will be glad to answer.
You have any questions? So let me ask a question, Sergio. So if you have multiple attributes, why would you use a bivariate density function rather than a multivariate?
No, actually, the bivariate, it's a special case of the multivariate. So since we have only two parameters, which is the multiple attribute utility and the total cost, we only have to use the bivariate. We don't have the opportunity to study a case with much more than two parameters, and I will explain why. Because when you have to, are you still seeing my picture, my presentation?
I can see your screen. It says Zoom.
Can you see it now?
Yeah.
Okay, let me come back to this picture. When you have bidimensional graph, in other words, when you have only two parameters, in this case, it's the multiple attribute utility and the normalized total cost, it's very easy to identify the Pareto front, for example, by inspection. Okay, you can only, for example, in the MATLAB application, you can click in the points of interest, the points that you are you intuitively think that are belonging to the Pareto front, and the MATLAB will identify those points to you. It's very easy when you are when you are dealing with only two parameters. But if you are dealing with many parameters, it's impossible to do that by inspection. You have to apply some brute force algorithm or genetic algorithm to identify the Pareto front. Okay, so we only applied our method to bivariate cases. That's why we are using the bivariate Gaussian.
Okay. No, but how do you decide on the weights of the multi-attribute function?
Good question. Actually, the original guys who proposed this case study used a committee of subject matter experts to assign those weights that you see here. Okay, 0.6, 0.3, and 0.1. It was assigned by
they're assuming that you have a linear utility function. What happens if you have a multiplicative utility function?
Actually, if you trace a graph of these levels and this single attribute utility, you are going to see that it's not linear. It's not necessarily linear. Actually, it's a exponential curve.
I understand, but you are combining the non-linear utilities using weights which are linear. So it's a weighted sum. So, but when you have, in Kini and Raifa's book, you see the multi-attribute means that the sums don't add up to one. The sum of the weights don't add up to one. That would be the case when this is they call it a multiplicative utility. It's not about linearity. It's about is an additive or is it multiplicative?
You are referring to these weights? Are you referring to this?
Yes. Those weights add up to one. Therefore, you have an additive utility function, multi-attribute utility function. But if you didn't add up to one, so I guess by design you decided to make it add up to one. That's the reason. But in theory, you could actually, because those weights will be obtained using some sort of lotteries, I presume. They don't have to add up to one. So have you studied that case?
They could have, I know that they used a committee of subject matter experts to assign those weights, but they could also have used the following method. They could have created dummy attributes For example, delta V for subject matter expert 1, delta V for subject matter expert 2, delta V for subject matter expert 3, etc., etc., and so on and so forth. They are dummy attributes, and applied to each one of these dummy attributes, the weights that subject matter experts thinks that the attributes have. Okay, it's actually the method of multi-attribute Tradespace exploration. It's well described in a paper by Professor Adam Ross, and the details for the results of our work, it's not, I think, very important. The great importance is the comparison of the result of the meta method with the ranking generated by the Gaussian AHP method. Okay.
So Sergio, just a curiosity, why do you call it Gaussian AHP? Where is the AHP component? Where is the pair comparisons here? I presume that the comparisons are in the weights of the attributes that you have here.
Okay. As I said, in the Gaussian AHP method, there is no pairwise comparisons. The proposition of the method. Let me come back to here. The method of the Gaussian AHP, what they do when they proposed this method is to produce a ranking by performing dot product, product of each point. In this case, the attributes of each design alternative in the transpose normalized standard deviation. And they don't perform pairwise comparison.
How do you the inner product of each point, in this case, each attribute of each design alternative. So each alternative has a value in the attributes. So what you're doing, you're multiplying the vectors and adding them up. That's what it is. So I understand that piece. So the question is why the word AHP comes into the picture. Because if it is not used, then it's not AHP. It's just the Gaussian multi-attribute utility theory problem. That's my question. So there must be somewhere where these attributes get weighted, and those weights are obtained by using an AHP method. That's using a pair comparison, because that AHP it requires a hierarchy, but let's assume there is no hierarchy. It's just pair comparisons. So that's my curiosity. I think that's what I'm thinking. But you have a hierarchy of attributes in AHP, the same as in multi-attribute theory. You have a hierarchy. You have attributes and you have alternatives, and alternatives are measured with respect to the attributes, and they have to be numerical to be able to measure them.
Yes,
so it's qualitative. Then you have to assign the value yourself, right? But this has to be, in order to be able to get a result, they have to be some numerical values.
All the values are numeric, and all the values are attributed by some subject matter experts. Okay, it's not to obtain it arbitrarily.
I understand that piece. I want you to think about how does the AHP comes into the picture. I didn't see that in any of the writings.
Okay, I think
maybe I'm not reading the right thing. Tell me what to read to see so I understand it. That's what my question.
You can refer to this paper, the Santos et alia.
Is that at the end of your paper? That reference?
Yes, in my full paper, the reference.
Okay, so if I go to the full paper, which I have here, let me see what that is, and I can find the paper, and I don't bother you anymore. Okay?
No, it's not bothering.
Santos Costa multi-category, a new approach to international journal. Oh, it's in the AHP model.
It's only
that I'll read it. Don't worry about it. It's my problem, not your problem anymore. Okay.
No.
Thank you.
Thank you very much for your question. For your interest. I think just for the sake of this presentation, we assume that the proposition of the Gaussian AHP method is assumed by default. Okay. If you have to discuss the principles of the Gaussian AHP method, we have to do a presentation about the Gaussian AHP method specifically.
Right. That's what my ignorance comes into the picture.
No, it's nothing. That's me. Oh, all right.
Any other questions? Any other questions besides my ignorant question?
It's not ignorant question.
I understand it. I understand.
Luis, I appreciated your question very much.
Thank you.